Hello everyone. So again, my name is Sergey Maschenko, and the topic of today's webinar is serial farming from A to Z. So let's see the outline of the talk. Set aside roughly 1 hour, so that should be the time I'll try to stick to. So the outline is to give you an introduction, to tell you what is serial farming, and in fact, more than just serial, we'll be discussing parallel farming, so to speak. I'll show you some examples where you might need serial farming. And then we'll talk over some simple solutions which can greatly help you to organize your workflow when you have to do serial farming. So we'll talk about some command line bash scripting basics, and also I'll briefly touch upon array jobs feature of scheduler. The idea is to spend most of my time talking about the advanced set of scripts which I wrote and you can use after this seminar is over. I call it advanced serial farming. And there is one set of scripts which cover different scenarios, and we'll discuss separately small number of cases, and I will tell you what I mean by case, and large versus large number of cases. And also I'll give you some practical examples how to use those scripts. And at the end, I'll give you some words of caution. So that's the setup, that's the idea. And let's start with the slides portion of my presentation. So let's start with the introduction. So what is serial farming? I don't think there is an official formal definition. You can look it up at Webster dictionary site, but my definition for today is running multiple instances of a serial code. And for the purpose of today's talk, that would correspond to serial jobs on a cluster when order of execution is not important. And that can be possible only if there is no data dependencies between the jobs. It is very trivial to extend that to cover batches of independent parallel jobs. Then you can call them MPI farming, OpenMP farming, GPU farming, and so on. You can say parallel farming in sort of to generalize. So when you might need to do any kind of farming, so I'll just cover a couple of common situations which I have personal experience with, and I'm sure some of you have some other examples when you might need to run those batches of independent jobs. So one common situation when the code output depends on some unknown or poorly constrained parameters, and your task is to find those parameters to either solve some sort of global equation or to find global maximum or minimum. And in the latter case, that would correspond to global optimization type of problems. So, and then you can have two different kinds of situations. If you have fairly small number of unknown parameters, let's say less than 5, then you can deal with grids. So you can start with a coarse grid covering multidimensional parameter space. You can sort of do brute force investigation using a grid approach. Using a two-dimensional simplified example, so the first point on this slide shows unimodal situation. If you know you have just one sort of global maximum, minimum inside your multidimensional parameter space, then you can have a grid, maybe having as few as 3 grid points in each dimension, and which results in a feasible number of code computation you need to do. What if you don't know how many modes you have, sort of multimodal general case situation? Then how many jobs, how many grid points to test? Then there is no answer basically, and it depends on how many CPU hours you can afford to spare for this project basically, if you don't know the properties, how many modes. Okay, if you have even more than 4 dimensions, things get even more difficult. And what typically is done, you do a sort of random guessing way of trying to feel your way towards some global solution or global minimum maximum. And that's called Monte-Carlo approach. In either way, either regular grid or Monte-Carlo approach, you can either just try to get your answer in a single batch of many independent jobs, which is often quite inefficient way of getting an answer. Often it's more efficient if you run one batch with coarse grid, Then you sort of zoom in into area of interest in your parameter space, and then reran another batch of independent jobs with another grid or another Monte-Carlo batch of jobs where you're trying to find more accurate answer. So anyway, that's one possible situation when you might need serial or parallel farming. Another situation I have personal experience with, when you have a large, usually parallel simulation code which has some time evolution of your system. In my case, it was cosmological simulation of dwarf galaxy formation I did a number of years ago. And you can see on the bottom the visualization of the snapshots my code produced. So once you have those snapshots, to do visualization is sort of a serial farming scenario because there is no data dependency between different visualizations. So you can organize this process of producing a snapshot images for your video as a serial or parallel farm. So that's another case. But I sure know some other situation when serial farm is essential and needed. So you know you need to do one of those things. How to organize your workflow to do it as least painful as possible. So let's talk about some simple solutions. And even though this talk was advertised as not only Sharcnet specific, I'm afraid some stuff will be Sharcnet specific. So if you would like to apply these ideas in other consortia, please talk to me, send me an email. I'll give my credential at the end, because things we discussed today will have to be modified somewhat. So one of the things which would have to be modified, my description depends on Sharcnet job manipulation scripts, which are SQSub to submit jobs, SQJobs to query jobs, and SQKill to kill jobs. So again, all this stuff can be modified to other consortia scenarios, but for now, it as written is Sharcnet specific. Plus, you will need some bash commands, loops, etc. I don't think I will have time to describe all the bash commands I'll be using, so I'm afraid some familiarity with bash scripting is needed. If you don't really know much about bash, the slides of this presentation and the video recording will be made available after this presentation. And we also have some bash tutorials available on our help section, our web portal, so you would have to probably go back, read some bash primer, and then revisit my slides or video recording to get a better understanding. SQSub command to submit jobs requires two obligatory arguments, -r runtime. In this example, it's -r1 day, and also -o, and then the name of the log file where the O output will go to. So these are required arguments. And then you provide your code, full path to your code, and then optionally arguments, command line arguments for your code, not shown in this slide. We will need at least one more optional argument for the SQSub. It's --ID file. The way to use it, to say SQSub blah blah blah, whatever arguments you're using, and then --ID file equal to the ID file. So what it does, so ID file is the name of the file which will be created by this SQSub command and will contain just one single line with job ID, the unique number identifying a job on this particular cluster. That will be the only content of that file. Let's see how we can organize your serial farming workflow using some very simple means, namely bash scripting and more specifically bash loops. So let's first consider the case for loop. This is convenient in the following example situation. When you have a code, you want to run multiple instances of your code with different initial condition files. Let's say your initial condition files, IC dot a number, and number goes from, let's say, 0 to 24. So this shown for loop, by the way, this is a single line bash command. I'm using the inverse slash sign at the end of the first line here, and this is the continuation line. When you type the command in your bash script, you can type it as a single line. What we see here, we have a for loop, which is using familiar C++ way of doing for loops. The only difference, instead of single brackets, for bash scripts, for bash loops, you have to use double circular brackets. That's the only difference for the loop arguments when you compare it to C or C++. But otherwise, inside you do the same thing and in C. I equals 0, semicolon, I less 25, semicolon, I plus plus. So this for loop will go sequentially from 0 to 24. And then you do semicolon, do, and then you provide command you want bash loop to execute. In this case, the command is sq sub, this obligatory arguments, minus R1 day, for example, minus O out dot. And then we use the bash variable, the loop index variable I, $I, to create output log file unique to each job. Then you provide code, full path to your code, and then IC.$I. So these are references to your IC initial condition file numbered from 0 to 24, if that's the way you organize your data. Semicolon, done. So that's example of a simple for loop which will submit 24 jobs to current clusters, and the output will go to separate files, out.0 to out.24, and the only command line argument for your code will be IC.0 to IC.24. So that's this very simple example of using for loop to submit serial farm. So this basically described the top point previously. Okay, so what more stuff you can put here? You can use this advanced --ID file option of sq sub to create ability to do meta job operations. I'll explain what exactly that means. So to achieve that, you add a few things to the previous example, and the differences are in a different color, so you can see what changed compared to the previous slide. By the way, $, just means prompt. So whatever prompt you have is just shown as $. And what you do first, you /rm ID file. Inverse slash means you remove, first delete a file, ID file. Then you say semicolon, and then you have the same loop as before. You add this additional sqsub parameter --ID file equal to ID. That's the new file you will create on each loop iteration. Then as before, code, etc. And then you add one more thing to do with semicolon inside your loop. So each iteration will print output of that ID file. Remember, that ID file will contain a single job ID. For each iteration, there will be one single job ID. And this double larger sign, which is actually redirect, will append the job ID for each iteration to one file, ID file. So at the end, once this loop is over, you will have a single file ID file with multiple lines. Each line of the file will contain job ID for individual jobs you just submitted, as described here. Why do you need that file? Now you have that file, you can have meta job operations. So let's say you have many jobs running, and if you want to do some operations aimed only at this particular serial farm, you can use that job ID in the following fashion. For example, you can list a status of all your jobs from this particular farm by executing the following command. So inversed quotation marks, if you don't know, it's a bash way of executing command and then substituting its output to some other command. So what happens here, cat job ID will print all the job IDs from the file we just created, and then sqjobs will receive a list of individual job IDs from a serial farm. So even if you have other jobs running, this command will execute only status of the jobs from this particular serial farm. Similarly, you can kill all the jobs belonging to this particular farm, or in other words, describe in this job ID file by executing sqkill and blah blah written on this at the bottom of this slide. So this is a convenient way of doing meta operation of your farm. So in principle, you can have separate serial farms, and you can operate with them independently. You can query them, kill them, basically these two operations. You can do that. Now, let's describe a different situation. What if you don't have initial condition files properly numbered from 1 to whatever, as we've seen in previous slides? What if you want to submit a job where your code would process a separate initial condition file, which is not properly numbered? They just all have different names. They might be even located in different subdirectories. For this, it's convenient to use different flavor of for loop command, as shown in this example. So what you do, you say for variable name. In this case, variable name is name, but it's a variable, in, and then you provide description which particular files you want to use. So for example, all your initial condition files have ic.something. So you can refer to them as ic.star. What this loop will accomplish, it will have multiple iteration, one iteration for each ic.file you have in the current directory. You can also use subdirector with star symbols. You can use question mark symbols. So you read more about Bash to know all the options here. But this is the way to submit one job per initial condition file you have if these files are not properly numbered. So inside your loop, each iteration will now have a $name. This is the variable which has the value is the name of your initial condition file for this particular iteration. So you can use that file name to create unique log output file name and provide it to -o SQSub argument. And also you provide as the, for example, command line argument to your code, if that's the way your code expects initial condition file to receive. So that's another way of using for loop in Bash. As before, you can add --id file SQSub arguments to be able to have this meta job manipulation ability. The next situation is typical for Fortran codes, which typically don't deal with command line arguments. Instead, they can expect standard input. So they want some standard input, which should be unique for each job, separate job in your serial farm. So using as example as before, for name in blah blah format, we provide a standard input to SQSub using SQSub argument -i. And then $name will be the unique initial condition file for each loop iteration, and which means for each job in this serial farm. So that's sort of more like Fortran-ish way of organizing serial farm. And yet another scenario, and this is going to be the most commonly used for the rest of my presentation. That's a really nice way to organize any serial or parallel farm, is to create a table. So you create a table, let's call it ic.dat. Each line of that table would contain all the information your code needs to run. So one line will contain all the information it needs. That information might have appearance of list of numbers or maybe some character strings. That can also contain full path to your initial condition file and so on. So anything the code might need can be put on a single line. So different lines of your table would correspond to different instances of your code in your serial farm. That's a really universal way of organizing farming. So we'll stick to that for the rest of the presentation. And the way to process such a table using simple Bash commands would be to use while loop Bash command. So let's see how it can be done. So in this particular case, we assume the ic.dat, your list of your cases or serial farm description table, has 3 columns. So we read them using while read command. After while read, you provide a list of variables which will read one line at a time from that table at the end of this command. And you provide the names of the variables where each column will go to. So as listed on the bottom of this slide, read ABC will read 3 columns into 3 separate Bash variables, ABC, one line at a time. So then you have standard do configuration, do loop. One more thing we do here, we initialize a variable I to 0 before the loop, and then we increment each iteration plus 1. I don't have time to describe why this particular command increments variable I plus 1. You have to read bash documentation. But that's how we have to increment a variable. And then you do standard SQ sub, and then that's assuming that your code expects to see 3 parameters, 3 arguments, as command line arguments. So code, $A, $B, $C. And at the end, after done, there is inverse redirect, this less sign, and then the path to your cases table. So that's how you organize while loop using one single table describing all the parameters your serial farm needs, one case per line. And let's consider the most complex situation we'll consider using a simple tools, single line bash script. Sorry, not script, a single line bash command approach. And that is, what if each time you run your code, it will create a new output file? This is a fairly common situation. So you don't want to run multiple instances of your code inside the same directory because the output will be overwritten. If the output file names is not unique, it's the same. So what you want to do instead, you want to create subdirectory. Go inside that subdirectory and then run your code from there. So each your case or inside the serial farm will have a separate subdirectory. So all the local files will be created in different subdirectories. Example at the bottom shows how we can implement that. So the differences from the previous example are shown in different color, in purplish color. So what we have to add actually 3 things. Or actually there are four additions or corrections. At the beginning of each iteration, you have to create a unique subdirectory name. In this case, we call them run $I. And remember, I is here goes from 1 to number of cases, from 1 to n. So this will create run 1, run 2, and so on. Then you do semicolon, then you go inside that subdirectory, semicolon. Then you submit a job. And once the job runs, it will run from that subdirectory. And then one more thing you have to add after you submit job, you have to cd to your root directory, come back one level up. If you don't do that, it will generate a problem. So you have to do that. And now we assuming here the code resides at the root directory, so you have to address it. The path to the code will be /code name. So you're running your each case inside one level down subdirectory, but to properly access your code, it should be /code, so one level up. So this is the most complex situation we consider using just single line bash approach. And it shows that it has limitations. It becomes too messy, too difficult to understand what you're doing when everything is on a single line. The better way to organize your workflow is to put all that stuff inside a text file and make it a bash script, which you can execute. So the previous example, if you write it as a bash script, looks much, much better organized, much more readable. So this is the content of your script, doing exactly the same stuff as before. So now we can properly organize, putting stuff on different lines of your script. So you can see nicely, you can use indentations to nicely put aside to identify stuff which goes inside your loop. But otherwise, it's the same content, just more visible, better organized. There is one special line at the beginning which you don't even have to put, but usually it's a good idea to put. All it does, it tells the operational system that this is bash script. So it's not Python, it's not Perl, it's not some other interpreter. This is specifically bash script, which is the default behavior for scripts in bash shell, but still it's a good idea to put it. And finally, once you create such a text file, it's a good idea to make it executable by using this command. And then you can run the script by saying /bash script name. So that's how you can execute your scripts. I don't have time to cover everything you can do inside bash scripts. I'll just mention that bash scripts can accept command line arguments. And for example, let's say you want to provide full path to your code as first argument, and second path is a directory where your cases table is located. So 2 arguments. So, and then you can execute as shown at the bottom of this slide. And modifications to the previous script example are shown in purple. So you add, so $1 would correspond internally to the first argument, $2 would correspond to second argument. You can assign them to variables with more meaningful names, let's say code and working directory, and then you just use them inside as you would use any bash variable. You can change to working directory, cd working directory, and then you can use full path to your code inside your sqsub command. So that's about bash scripting. I'll briefly mention another way of doing serial farming is to use an array jobs feature of schedulers. I just mentioned there is such a possibility. We don't actually recommend for a few reasons I won't go into. But if you need to know more about it, I'll give you a link in a couple of slides. So basically, schedulers like our torque scheduler we use in Sharcnet accept job arrays, or actually they call it array jobs. And how you do that, you actually still have to provide you have to write and provide a script to the scheduler. So you don't submit your job, you submit a script. And then you submit your job meta job or serial farm as a special array job. Inside your script, there is a special environment variable, which I call $rank, but usually it's probably a different name, depends on the scheduler, which the task of your script is to read the value of that variable and then run your code accordingly. So you use a rank number or ID number of your job within array to maybe read a separate ID file, or initial condition file, or to read a line from a cases table as I shown before. So you still have to do some code and some scripting to avail the array job feature. Complication, this array jobs feature is not available through our SQ wrapper approach. Instead, you have to use directly this underlying scheduler command, CUDA. And because we don't really have good tutorials how to use underlying scheduler, that's why the main reason I don't recommend using array jobs, because you have to learn a lot of things which are not actually explained well on our help section. I'll just briefly mention when you submit array job using CUDA, not SQ, but CUDA, you use -t, and then you provide a range of array indexes, let's say x-y. That's about it. So if you want to read more about array jobs in Torque Scheduler, the one we're using, please check that link. But as I said, this is not something we recommend for a number of reasons. So instead, let's switch to the most important part of my presentation. Let's talk about a set of scripts I wrote for advanced serial farming. So what is lacking in the scripts or commands I described so far? So it's lacking some more advanced features which would really make your life easier. For example, if you run hundreds, thousands of serial farming jobs, it is the reality. Some of those jobs will fail for whatever reasons. The node can be corrupted some way. Maybe home is not mounted, global work is not mounted. Maybe node will crash when you run it. Maybe the whole cluster will go offline. So some jobs will crash and some will finish properly. So what is lacking in the previous examples, how to track the status of all the serial farming jobs. You want to identify all the jobs which finished properly versus jobs which failed for whatever reason, and versus jobs which never ran for whatever reason. So that was lacking. Ideally, you want to have that kind of statistics, and you want to have a situation when it's easy to resubmit jobs, all the jobs which never ran or failed in one simple command. So that part is lacking. It's advanced feature. Another advanced feature which is lacking is the ability to use multiple clusters simultaneously, so-called meta cluster or grid mode of operation. So that is lacking, and I will cover that later, and I'll tell you why you might want to do that, why you might want to use multiple clusters. And third feature is the situation where you have many, many very short jobs, maybe thousands, tens of thousands. It's very hard or even impossible to submit very short so many short jobs in Sharcnet. And if you do submit, they may be very inefficient. because of overheads of scheduler. So the better way to organize such serial farms is to have sort of meta jobs. So each job would process not just one case, but multiple cases. This advanced feature is missing in the examples showed so far. Don't worry, you don't have to spend hours and days of advanced scripting. So I've done the job for you. So I'm providing scripts which will do all those advanced features and more. So without really much work on your side. So let's go into details. So first of all, let's formalize. What I call a case is a single execution of your code in a serial or parallel farm. It doesn't have to be serial code execution, maybe a parallel. GPU execution, maybe OpenMP or MPA. Let's call it a case. And why I differentiate now? Because now we'll have situation when there will be multiple cases per job. So you have to separate a definition of job from definition of a case. So let's first consider a situation where you have smallish number of cases. It's not exact number. Let's say roughly less than 500. You know, there is not exact science. It's not precise. But let's say consider a situation, fairly small number of cases, maybe less than 500 or so. In this case, it is convenient to dedicate a separate job to each case, the way it was described so far. So no much difference in that regard. So the set of bash scripts I wrote, they handle all kinds of situations, including this small number of cases situation. So, but you only need one set of scripts to do any kinds of serial farming. To start, you have to copy the whole set, the whole directory containing multiple scripts, by copying these directory inside my home directory in Sharcnet. So you SSH to one of our clusters and copy the whole content of the following directory: sam serial farming dash meta. This is readable for all users. If you want to run multiple serial farms independently, you will have to that copying a few times, once per each serial farm you want to execute. And in that case, you would have to copy them into separate subdirectories with separate names. Let's say meta, meta1, meta2, and so on. There are multiple scripts inside that directory. The two essential ones are submit.run and single case run. So submit.run has two obligatory command line arguments. The first line is a pass to the cases table. So at this point, you should have a good understanding of what I mean by cases table. This is a text file where each line of the file would have all the information one serial farm instance execution of your code needs. For example, it would contain command line arguments, would contain potentially path to initial condition file, or anything your code needs to know to execute for each case in your serial farm. So in this case, we consider for now small number of cases, or one case per job scenario. The second obligatory argument of submit.run script is just -1. So it's just -1. And -1 basically switches my scripts into this one case per job mode. So there is another script called single_case.run. And this is the only script which might need customization. But in many cases, you don't even need to do any customizations at all. The task of that script is to read one line of that cases table, to parse it, and to provide all the information your code needs to execute one particular case. The default version of single case run also creates individual subdirectory with the name run YYY, in this case YYY being the case number. So if you submit serial farm with 128 jobs, it will create 128 subdirectories, run 1 to run 128 inside the current directory. I'm showing what's inside the single case run default configuration. So it shows you what it does. It creates this run subdirectory, it goes inside it. It executes the content of the cases table line, one single line. And that's how you execute it in bash. And redirects all the output into a log file, which will reside inside subdirectory, which all have unique. So each case has unique subdirectory, so they all can have the same log file name. That's not a problem. And very important, don't really change this. This should stay the same. We capture the status, the exit status of your code execution. This is crucial. This will be used in this in the analysis of your job output to figure out which jobs failed and which jobs never ran. And that is required if you want to resubmit jobs which failed or never ran. More about that later. So your cases table can look like this. So anything which can be parsed and used by your code can become a line, one line of that table. So anything which can be, so in the default configuration single case run, it expects the first argument to be actually the path to your code, or the name of the code if your code is on your path environment variable. So it can be executed from any directory or subdirectory. So anything of that kind can become a line in your cases table. One warning, a note, once you write your submit run first time, it will append a line number at the beginning of each line. Don't worry, it doesn't mess up at execution. It will execute just fine if you execute second time, third time, and so on. It just will prepend a number, 1, 2, 3, etc. This is used internally by the scripts. So as I described, the $status variable is important. It needs to be defined properly inside single case run. And I will show a situation on this particular slide. You can actually append and modify single case run. So what default configuration does, it captures the exit code from your exit status from your code. And that might be sufficient or maybe not. Sometimes your code exits with exit code 0, which normally means correct execution, but something went wrong inside your code. So it is possible. Some codes don't do full exit code thing properly. So you can modify the single case run script to add some more knowledge about when is your case execution failed. For example, you know that if your code run properly, it should produce non-zero output file, let's say out.dat name of the file. So you can add these purple lines inside a single case run to add this more intelligence. So what it does here, it tests if after your code execution there is no non-zero size file out.dat, then it will say status equal 1. So even though exit status can be 0 from the bash shell perspective, but you added some intelligence to tell it if there is no such a file exists at this point, the status should be actually 1. 1 means failed. This is important to add if you know this extra information about code execution, so you can easily figure out which jobs failed and which didn't. Anyway, so submit.run also creates some other auxiliary files. I won't go into details. You normally don't need to know about those files. And there are a few other scripts. So there is list.run, which just lists all the jobs running in this particular farm. There is a query run, which more or less the same, but collapsed to a single line, just statistics, how many jobs are running, how many jobs are queued, how many jobs are done. There is a kill.run script, no arguments. When you execute inside that meta directory, it will kill the current serial farm jobs. Prune.run, which you normally don't run yourself, it's been used by other scripts. Status with capital S will list all the jobs one line at a time with the status either 0, which means it finished properly, or non-zero if it didn't finish properly. So the exit status will be displayed one line at a time per case. And finally, this is very important, resubmit run. Resubmit run accepts exactly the same arguments as submit run. So you run resubmit run after you submit run serial farm finished. In fact, it has some protection inside. If your serial farm hasn't finished running yet, you won't be able to run resubmit run. But once it's finished, you just do resubmit instead of submit with exactly the same arguments as before. And what it does, it's analyzing all the jobs in your serial farm, finds all those which failed or never ran, creates a new cases table only for those jobs which need to be run again, and resubmits them as a second serial farm. That's what it does. So no work on your part is required. It's going to be happening automatically. So which is a great convenience. So that's exactly what I described so far. If you still couldn't finish your large serial farm, even if after you run resubmit, you can run resubmit run again once the previous resubmit jobs finished running. So when you do that, you repeat exactly the same arguments as before, and again it will reanalyze the output, again find everything which still failed or still didn't run, and will run as yet another serial farm. So it's a great convenience to just run, wait until it's finished, run again, and eventually if there is nothing to run, everything finished properly, it will tell you nothing to run. So don't worry, nothing will be submitted if there is nothing to run. Okay, that was a situation, a single cluster usage. What if you want to use multiple clusters? So just let me mention, why would you want to do that? Users often make a mistake in Sharcnet using only one largest cluster we have, which is Orca. And this is bad. In fact, it's so busy now. One of the reasons it's so busy because everyone considers to be the cluster to use. And second, because Orca is heavily subscribed by NRAC, National Research Allocation projects. I believe maybe around 80% subscription level for this year. So it's almost impossible to run anything unless you run an NRAC jobs on Orca. You should be aware we have many other clusters. Well, not too many, but quite a few resources are available outside of Orca. But it's a bit cumbersome. You have to SSH to different classes, try to run your farm there to see if it runs quickly or not quickly enough. What ideally you want to have in this situation, you want to have grid computing. So you say, I want to try, here's the list of the clusters I want to try. And usually don't put Orca there because it's really not really usable for serial farming. So here's the list of clusters I want to try, like Kraken, SAW, and we have some contributed systems which are fairly large, very usable. And you want to submit jobs to different clusters for the same serial farm. And it basically asking the script, please find the resources which are the most readily available and run a certain number of jobs on those clusters. Doesn't matter where. So this is sort of grid computing. And this functionality is built into my scripts. So let's consider how it works. So by default, it doesn't work. By default, my scripts run on a cluster where you log in. If inside that meta directory you create clusters.lst file, and if inside that file you list clusters, one line at a time, and then you run your submit or resubmit commands, it will automatically switch to meta cluster or grid mode. Let's say you put inside your file, clusters.lst, you put Kraken, SAW, and Redfin. These are three. So two are general purpose, and Redfin as one of the contributed system, which can be very usable for serial farming. You don't have to include the local cluster. So you can run this script from Orca, and you don't have to include Orca. So you can run the script from any cluster in Sharcnet. So let's consider the situation, this small number of cases, -1. That's what we've been discussing so far. One job per case. So if you do that, -1, and provide clusters.lst file, so what will happen? It might be a little bit confusing, but just bear with me. So what will happen? It will submit a certain factor. In default situation is a 2 times number of cases, number of lines in your cases table across all the clusters in the list. So let's say your cases table has 100 cases, 100 lines. If you use -1 argument to your submit.run, and if you don't have clusters.lst file, the script will submit 100 jobs on this current cluster, which is totally sort of reasonable behavior. That's what you expect. 1 case per job, so you want to have 100 jobs to run on this particular cluster. But if you provide multiple clusters on .lst file, it will actually submit twice more jobs globally across all those clusters. So if you list, let's say, 4 clusters, and you have 100 cases in your table, it will submit 200 jobs across 4 clusters. So each cluster will get 50 jobs on average. So why to do that? This is to enable this greed behavior. So we have to overcommit a little bit by some factor to actually be able to run number of jobs we want, which is 100, on some clusters. We don't know which ones, those which are the most readily available. So you need to have this overcommit factor, and default value for this factor is 2. And please stick to that factor, which is, it should be a reasonable factor. So don't be surprised when you use this -1 argument and you provide clusters.lst file, you will see the job, the script, sorry, is trying to submit twice more number of jobs compared to number of cases. Don't worry about those cases or jobs which will never have anything to compute. Only the very first n cases jobs will actually do computations. The rest will very early on will get pruned, which means they will be removed from schedulers while still queued, or those who manage to get through the schedule will die instantly. Should be a very tiny minority. So mostly of those jobs which never run, which in this case is 1/2 of jobs you submitted, they will get pruned. So this is how it works. The very first job which will actually run on any cluster will request a case to process. Initially, it's going to be case number 1. Second job to run will ask for the next available case will be case number 2. This is an interesting situation. So you don't even know which job will process each case. Whatever becomes available next or runs next will process the next case. To accomplish this interesting and very convenient feature, one needs to serialize certain operations, which means all those jobs need to do a certain commands only one job at a time in a serial queue. Specifically, each job should be able to do serialized read currently served case number from a file somewhere. Then this job can use that case number for its own computation, but also it should do to update it +1 and write it back to the file. So only one job at a time can do these 2 operations. So how to accomplish that? It's not actually a trivial thing to accomplish. How to make sure if there are multiple jobs trying to do the same things at some random moments of time, how to make sure these 2 operations are protected, serialized. So we have to use a trick, and the trick is being used is a log file routine. It's a small binary which I provide as part of my scripts. You can find it inside the matter package. You have to do one thing once you copy my files. You have to place that log file on your path variable. And here I just describe how to do that. If you don't have your local /bin subdirectory on your home file system, you create it, then copy log file there, and then you append your .bashrc file to put that directory on your path. Once you do that, that log file will be available anywhere you execute it. You don't have to provide full path. So what if you have more than 500 jobs? You still can use the previous example, maybe 1,000 jobs, 2,000, maybe it's going to work. It's going to be slow. Look at the second point here. If you need to submit 5,000 jobs, it takes some time per job submission, maybe 2 seconds or so. Sometimes schedule is very busy, it can take even longer. So you might end up spending 3 hours just submitting your serial file, which is very inconvenient. Also, clusters have limit how many jobs you can queue, because if you submit too many very short jobs, it will pretty much overwhelm the scheduler. So for Orca, the limit is 5,000. So what if you need to process 10,000 cases? What to do? You can. So previous case won't be able to help you. And finally, when you have many, many cases, thousands, that typically means that each individual case is very short, maybe less than 30 minutes. And if that's the case, if you organize one case per job, and the case is, let's say, 10 minutes long, each job submission and finishing the job has some certain overhead, maybe 30 seconds, maybe more, maybe less, depends how busy scheduler is. So you can imagine you're wasting quite a bit of time by submitting lots of very short jobs. So with large number of cases, you want to be able to do things differently. Namely, you want to have ability to execute multiple cases per job. My scripts handle that situation. So how to do that? well, there is a special different mode of operation. I'll describe it in the next slide. But one of the things you really want to do when you have a bunch of very short duration cases and few jobs handling those much larger number of cases, you want to have dynamic workload balancing scheme. Why is it so? It might be the case that some of your cases run shorter, take shorter amount of time to execute. Other will take longer amount of time to execute. Also, especially if you use multi-cluster mode or meta-cluster mode, some of the CPUs might be faster, other CPU might be slower. So even if you try to statically distribute equal number of cases per job, some jobs will run much sooner than the others. So there is some disbalance, workload disbalance. So instead, one would have to use dynamic workload balancing. In my scripts, utilize that internally. You don't have to do anything special. It's automatically done for you. And I just have two colorful slides to demonstrate how it works. You submit n, I call them task jobs or task.run jobs. That's the name of the script which is actually submitted. And this case is n. So each job does a few things. Let's say I'm job number 1. I have a loop inside. So I go over multiple cases. Each task run goes through serialized queue. Remember, I described how to use log file to organize serialized protected part of this script. Only one job at a time can do that. To get next available case number. And then once you do that, you run single case run, which runs user code exactly the way I described before. So the difference is now there is a loop. So each jobs will go over multiple cases using the serialized queue. And this it actually enables the dynamic workload balancing. So whatever job which is the fastest gets the next available case number. So some jobs maybe running on faster CPUs will go over more iteration inside the loop, so they will compute more cases. So how it exactly operates, the dynamic workload balancing is visible at these slides, on this slide. So in this case, there are 4 task run jobs, and they compute 22 cases. So as you can see here, this is time, this is arrow, this is the direction of the time evolution. So as you can see, initially jobs grab whatever is available, case 1, 2, 3, 4. But then the job which finished its own first case sooner will get next case 5. And then it will get next available, and so on. So as you can see, regardless how short or long individual cases might be, all the task run jobs will finish roughly around the same time. Even more interesting, the jobs don't have to start at the same time as shown in this simplified diagram. In fact, reality is different jobs always start at different time. It doesn't matter. The dynamic workload balancing scheme makes all your computations, the whole serial farm, finish around the same time. This is the best possible scenario when you want to get your whole serial farm results as quickly as possible. So this is really perfect situation for serial farming when you have to compute many cases and get your result as quickly as possible. So to enable these multiple cases per job mode, the only change you need to do when you run your submit.run or resubmit.run, instead of -1, the second argument should be the number of jobs you want to run. In this case, the number of jobs will be much less than the number of cases. So this is the number of task run jobs. The jobs will actually run, and those jobs will eventually process all the cases. It doesn't matter how many of those jobs will actually run. This is the beauty of this approach. If the clusters are very busy, only some of those jobs might be able to run, but still, all your cases will eventually be processed as long as you manage to do that within a 7-day runtime limit of those jobs. So now, number of jobs you actually submit. Again, there is this ×2 overcommit factor if you use clusters.lst file. So if you submit to more than one cluster, you end up submitting not 32 as shown in this example, but 32 times 2 to all the clusters in the list, so across all of those clusters. But you should be aware that there is limits built into the scripts. So you cannot have more than 256 jobs running anywhere in Sharcnet at any time. So with a factor of 2 overcommit, which means you can only submit up to 512 jobs across all the clusters in the list, in your list file. Only half of those jobs will ever be able to run because you have that 256 running job limit. I'll just describe a couple more slides, and I'm afraid the rest will be probably left for you to read the slides. Slides will be made available. So the simple user scenario. So how, in practical terms, to start using my scripts? First, you copy directory listed here to your file space with all its contents. And by the way, it's very important to use global work or global home, but still preferably global work. Don't use Scratch. Don't use /temp or some other file system. You need to use file system which is visible from all the cluster and from all the compute nodes. Next, you put log file utility in your path, as I described on slide 45. Copy your code initial conditions to that directory, which is optional, or you can use full paths for both your code and initial condition files. Create a cases table, one case per line, as described before. You can have multiple serial farm directories if you want to run multiple farms. Then you modify, if needed, the single case run script. If you want to use meta cluster mode, create cluster.lst file and put a few clusters you want to use. Please don't put requin. It's not compatible with the script. It's using a completely different scheduler. And it's a good idea to initially run on a single cluster without cluster.lst file with just a few jobs to see if everything works. A couple of words, what if you have to use advanced SQSub features? What if you want to do parallel farming, if your code is actually parallel? You can pass all the SQSub arguments to my submit.run, resubmit.run scripts by appending them as last arguments on the command line. So as shown here, you can add -q MPI -n4, and then submit.run will pass along those SQSub arguments to SQSub commands internally. Or you can add -r at the end. By default, my scripts assume 7-day runtime limit. If you want to make use shorter runtime, you can modify that by appending -r arguments at the end. And I'm going to skip this threaded example. Let's say MPI farming. What if you want to do MPI farming instead of serial farming? You have to add those, at the very least, you have to add these 3 SQSub arguments at the end of my submit and resubmit scripts, list of arguments. You have to add -q MPI, you want to use MPI-Q, -n number of CPU cores you want to use per job, per case. And you have to say -- no MPI run. I don't have time to explain why. And then you either modify single case run by prepending MPI run before this standard line you have in that script. So that means your code will have MPI prepended. That's the way you have to run MPI code. You have to say MPI runs, period, blah, blah, pass to your code. Alternatively, you don't have to modify single case run. You can prepend MPI on each line of your cases table. And just words of caution, I have to mention that. So please use common sense when using meta cluster mode of the scripts. Remember, there is an overcommit factor, so you submit more jobs than you ever need for that particular farm. And the factor is 2, but still you have to use your common sense. You have to be careful. So there is overcommit factor constant, which is defined to be 2. It pretty much forces you to behave reasonably with a common sense. So you probably shouldn't think too much about it. We built all the safeguards in the scripts. What you want to do also when you submit your jobs, frequently run the query.run script. I mean, frequently, not every second, but maybe once every 5-10 minutes, or once every hour, depends. So what it does, it informs you of the health of your farm. It's good to know if something goes wrong, you want to do something about it. But also very importantly, once the script figures it out that those excessive overcommit jobs are no longer needed, they might be still queued, or maybe they're already running, it will prune those. So the jobs which are still queued and it detects that they're no longer needed, it will remove them from all the clusters it's been submitted to. So the pruning step is also important to make your scripts as Sharcnet friendly as possible. So please use query.run script more or less frequently. Please make sure your code only accesses /work or /home. These are the only file systems which are visible from all the compute nodes on multiple clusters. This is crucial if you're using multiple clusters, meta-cluster mode. As I mentioned before, please start with much smaller test farm run. Make sure everything works. Stay away from Orca. It's not really good for serial farming and very busy because of NRAC jobs. Don't use Requin. It's not compatible. Rec scripts are not compatible with Requin. I don't have time to describe contributed systems. You can read it later. Finally, you can always contact me directly, sam@sharcnet.ca, if you need any help with job farming in general or meta scripts in particular.